Okay, we're almost ready to start and we're almost all here. Before I get going, are there any questions, anything that needs to be cleared up about what we've been talking about so far? Okay, great. So everything is more or less on track. We got another minute or so, and we still have one more to come. Hope everybody is staying healthy and relatively sane in this shelter-in-place time.
You too, sir.
It does go a bit stir crazy. Okay, it's 9 o'clock and time to start. So let's get going with today's class. Okay, for the next few times, I'm going to be spending most of it walking through certain models. Today I'm going to start catching up on a model that I started last week but did not finish. So that's the simple inventory model. And then we're going to expand the multiple server queue into the situation where we have more than one type of server. And then talk about the use of containers as part of the state. And then apply that to be able to explicitly tally the times, specifically the times in the queue and the times in the system. Okay, the inventory model with back orders. That's you can review last week's slides to see basically what this is about, but the idea is that you have this periodic review. And in other words, the inventory is not being continuously monitored, but only checked every so often. The situation is that you have these times between demands, and that's similar to the arrival process that we've been talking about. But the difference is that every time there is a demand, that is, every time a customer comes in, there is a certain number of items that are going to be demanded, and that's represented as a sequence. I'm calling D for demand. And in the implementation, that would be modeled as a discrete random variable. That is one that would have an integer number of possible values, but the particular sequence here, which is left unspecified, would just be, say, the first customer would want 3, the second customer would want 2, the next customer would want 5, etc. So that's unspecified. The next parameter is a sequence of lead times for the orders placed. In other words, when the facility runs, the review happens, and you notice that the net inventory is below this trigger point, that is the small s value, then you place an order. And the order that you place would be one that would put your net inventory up to the big S, the order up to amount. But then when you place that order, the lead time is the time between when you place that order and when the order arrives. The TR parameter is the time between reviews. Again, and that's, notice that does not have curly braces. And that's because the way it's being it's typically implemented is that that would be a fixed quantity, like it might be every day or every day at 8 in the morning or every day at a certain time or every week on a Monday, say, that the review would be done. The final parameters would be the initial inventory, I sub 0, and then basically the two decision variables, which would be the big S, the order, how much we're going to order up to, and the little s, which is the trigger quantity. In a sense, the third possible decision variable would be the time between reviews. That is, you could choose to review the inventory at a more rapid or less rapid pace. All of the other parameters are actually kind of outside of your control. Okay, the state variables would be the amount on hand at any given time. So that would be either 0 or some positive quantity. B would be the amount that's back ordered. And again, that would be either 0 or some positive quantity. And then T, the capital T, would be the total amount that is on order. In other words, that's the amount that we have outstanding. So B is the amount that we owe our customers. T is the amount that our vendors owe us. N would be the total number of items ordered. And again, that's going to be something which keeps increasing. And likewise, NO would be the number of orders. So N number of items, NO total number of orders. And that's something which is actually of interest at some point. So we'll hopefully keep track of that. Now, what I did not get to last week would be the next step, which would be the events. So let's take a look at the events. Now, the way to or the suggested way to proceed once you've defined your parameters and state variables is to look at all of the state variables and identify what could make them change. And the place to start is always with the run event, because the run event always initializes your state variables to their initial values. And there must be initial values for your state variables. Now, we say must. I mean, if you're defining the model and you forget to do that or you neglect to do that, then the state variables are not completely defined. In other words, a state variable is only completely defined when it is when its initial value is specified. Okay, so starting with the run event, the initial on hand I is the initial. Our amount on hand is our initial amount, that I sub 0, and again that could be any number from 0 up to some arbitrary value. And all the other state variables are going to be initialized at 0. The number of back orders, we're going to assume that we have no back orders at the beginning. T, the total amount that's on order, we're going to assume that we just kind of start fresh. Okay, so that's the run event. Now, what could happen? What could affect our variables of I and B? Well, the first would be a demand. So when we get a demand, remember that the customer will demand a certain amount. You know, here's the thing: is that what do we have to give them? If at any point there's a demand, we have I on hand and B back ordered. So I minus B would be the net amount right before the demand. And that could be a positive or a negative number. And then when the demand occurs, that net value would be decreased by this value D that the customer has brought on. And so what we're doing here is we're actually defining a local variable, that is this variable net. It's not a state variable or a parameter, it's simply a local variable just for convenience. It is, strictly speaking, it's not necessary, but it just helps with the computations in this case. So, or actually alternatively, and I'll leave this as an exercise, we could do away with that entirely, but add some more events to perform these computations. Okay, so but is it, hopefully it's clear that after the demand, our net value is going to be either positive or negative. So what can be helpful is to just sort of stick some numbers in. So supposing we have, let's say, supposing we have 5 on hand, no back orders, and the customer comes in and wants 2. So after that, the net would be 5 minus 0 minus 2, or 3. So we would have 3 on hand at that point. Now, our inventory and our back order then could be computed from this value, and that's a typo. That should be net. The X, I don't know how the X got in there. Darn it. Lost my mouse. Where are you? Darn it, you're it's covering up my screen, so I can't reach. This is so frustrating. I can't get to my annotations because this is blocking it. There, get out of there. All right. All right, this X should not be there. It shouldn't. Okay, so you know, they make these things so user-friendly that you can't use them. Come on. All right. So the net would be okay. So let's put another value in. Supposing again we had 5 on hand and no back orders, and the demand was for 10. So now we have 5 minus 0 minus 10, and so the net would be a negative 5. So the amount on hand, the maximum of negative 5 and 0 would be 0, but the maximum of negative 5, which is 5, and 0 would be 5. So after that, we would have 5 on back order. Let's see, advance the things. 10. Come on. All right. So, all right. So let's look at something else. Let's look at an order. We'll call it place order. And A is going to be the amount of the order that we place. So that's going to affect the state variable T, which is the total amount that we have on order. So that's going to, if we place an order and pass an argument of A, that's going to increase our total amount by A. And it will increase the total number that we have put on order by A as well. And it will increase the number of orders that we've placed by 1. And then the final state that might change things, if we have an order arriving of size A, then we now have A less than amount that we have on order. So if we had, so let's say we had 20 on order and we got an arrival of 10, then we now have 10 on order. And again, we do the same kind of calculation with the net value. So now this should be a minus. This should be minus B. So the net would be the amount that we have on hand minus the back orders plus the amount that we've just arrived. And then we have the same thing going on there. And of course, I copied and pasted, so that's happening there. But what about the reviews? Now, the thing about this is that we have a situation where our we have an event that we need to take place, and its only purpose is to schedule, possibly schedule things. In other words, when we place the review, that's when we decide whether or not we place the order, not at the demands, but at the review. So the final event graph looks like this. So we have our run and our state transitions, and we schedule, let's just look at the demand piece. So we have an event called demand, and that we looked at before, and it will be scheduled first with a time of arrival, and then every time there's a demand, it's going to schedule the next one. So this is like the same structure as that arrival process that we had. And in fact, if we wanted to drive this outside with an arrival process, then we could omit this entirely, but we would still need these state transitions here. So now for the review piece, here's the review is going to be scheduled every T sub R time unit. So the first one is scheduled, we'll schedule it at T sub R, and then thereafter it will keep getting scheduled at time T sub R. Okay, so now here the a lot of the mechanism is on the scheduling edge here. So let's take a look at this. First, the condition. Remember, after at this point of the review, I minus B is our net inventory. That could be positive or negative, but we also have T on order. So the thing is that our total net inventory position, that is not what we have on hand necessarily, but what we have on hand plus what we are owed, if that total is less than our trigger point, then we will place an order. Now, how much do we place the order for? Well, remember, at that point where we place the order, we want the net to be S. So in other words, if this is less than little s, we want big S minus our amount on hand plus the back orders minus the total amount that we have, and that's the amount that we place the order for. And then when the order is placed, then we have the state transition, and we schedule the order arrival with a delay of lead time passing at the value A, which is the amount that has been placed. And the reason this is an illustration of how using the parameters is kind of more essential here as part of the state, because every time we place an order, our net, the amount that we're ordering, is going to be different each time. It's not that we order the same amount each time. Now, in other situations, say we might have to order maybe in multiples of 100. Like we can't just order one, we have to order a group of 100, or maybe every time we place an order, it's going to be exactly the same quantity. That, again, there are models like that, but in this particular case, the amount that we order is going to change each time. Okay, so now on to the next model. Okay, so the idea here is that we have two types of servers. And our assumption is that the customers prefer the type 0. So we're going to use, again, the Java zero-based indexing. And so we have a type 0 server and a type 1 server. Customers prefer the type 1 server, the type 0 server, but they will accept a type 1 server if the no type 0 servers are available. Maybe like one way to maybe think of this is, let's say the type 0 servers are the express line in a supermarket, and the type 1s are just kind of the regular ones. And so if you have fewer than 12 items, then you would prefer to go through the express line. But if the express line is busy and there's a regular cashier that's available, then you're not going to wait on a line when there's a cashier available. Okay, is that kind of clear? Now, what's a little different than the supermarket is that because this is the same situation as a multiple server queue. In other words, there's only one line. Okay, so all the customers wait in the same line. And one of the things that might make this different is that the type 0 servers may be a little faster. In a fabrication environment, you might have uh, a set of machines, and you might have faster machines and slower machines, all of which perform the same task. So when a job comes in, you want to put it on the faster machine because it'll get done sooner. But if all the fast machines are busy, and there's a slower machine that's free, then you don't have the part just kind of sitting there. You put it on a slower machine. Okay, is that clear? Okay, so let's look at parameters. Now, this is similar to our multiple server queue case, but now should be, and in a way, kind of similar to our tandem queue case, but in this case, everybody, they're all kind of the same. There's just one. You just have to get one service, and it can be from a type 0 or a type 1. So, but we have K0 type 0 servers and K1 type 1 servers. And likewise, the service times for the type 0 servers and the type 1 servers are different. So we'll call these TS0 and TS1 for those service times. Now for state variables, these should be the available. Okay, so S0 would be the number of available type 0 servers and the number of available type 1 servers. I don't know, this all looked perfectly fine when I was checking it over. Okay, so S0, the number of available type 0 servers, initially K0, and S1 would be the number of available type 1 servers, which would be initially K1. Okay, so now the events are going to be kind of more or less what you might expect, although, okay, so let's, again, we start with run. Our queue, we start with 0 in the queue. All of the S0 and S1 servers are available. And then let's say what could cause queue to change? Well, one would be an arrival, and we increment queue. Again, we've been doing that almost since day one. Okay, but now we need to distinguish between whether we're starting service on a type 1 server or a type 0 server or a type 1 server. And now the start service 0, the 0 is part of the name. This is not a parameter. This is part of the name. And so if we were to start, what would cause queue to change? Well, one would be to start service on a type 0 server, and the other would be to start service on a type 1 server. And that also, if we start service on a type 0 server, we have one less type 0 server available. And if we start service on a type 1 server, we have one fewer type 1 servers available. And so now those are how S0 and S1 could possibly change. And then the last way they could change would be to increment. So if we end service, and this should be an end service with 0, there should be a 0 there. And that causes us to increment. Okay? And likewise, n service on 1 would increment the number of S1 servers. Okay, so these are all the events. And connect as far as the scheduling goes. So let's look at this from the back end first, because that's basically what we've done. If we start service on a 0, we will schedule an end service. I should call it end. I mean, actually, there's nothing wrong with leaving it without the 0, but this is just the way it should be. Okay, so a start service on server 0 will schedule an end service with a delay of the service time for that server. And then when there's an end service at station 0, if there's somebody in the queue, then it will schedule a start service at that station with that server. And likewise, if there's a start service on the first server, it will schedule an end service with a delay of specified by the service time at the first server, server type 1. And then after the end service, it will schedule a start service if there's somebody in the queue. Okay, so I took those first because those are exactly analogous to the multiple server queue that we've already talked about. So now here's where things get a little tricky, and where we have to utilize that preference for the customers, because we have to do something here. Because if we have an arrival, well, there are 4 possibilities, I think. When if the arrival when the arrival occurs, let's say one possibility would be there are no servers available at all of either type. Then nothing gets scheduled and the increment in the queue just stands. The second possibility would be if there is a type 0 server available, but all the type 1 servers are busy. Okay, in that case, it's pretty clear we would start service on the type 0. The third possibility is that all of the type 0 servers are busy, but there's an available type 1 server. In that case, we would schedule a start service on the type 1. Okay, so all of that is fairly straightforward. But the fourth possibility is that there is both a server of type 0 and a server of type 1 available. Now, if we're not careful, an arrival might schedule a start service on both of them. And as you might imagine, that would kind of cause problems unless you're schizophrenic or something. Okay, so here's where we have to capture the fact that the customers prefer the type 1 servers. And so if there's a type 0 server available, and that's this condition right here, if that's the case, then you will always start service on a type 0 customer, type 0 server, period, regardless of whether there's a 1 available or not. So this condition is sufficient. Just, is there a type 0 server available? That's the one that I prefer. And so therefore, I will schedule the start service. Now, you have to be careful not to schedule one on of a type 1 if that's the case. So we have 2 conditions here. First is an arrival will schedule a start service on a type 1 server only if there is no type 0 servers available, only if there are no type 0 servers available, and there is a type 1 server available. Okay, that's this Boolean condition. As you can see, it has 2 parts, and a Boolean expression can be as simple or as complicated as you like. So far, we've only seen simple ones like this one, S0 bigger than 0 or Q bigger than 0. But this is definitely not only a possibility, but in this case, a necessary one. Because without this first condition, S0 equals 0, an arrival that finds both type 0 and type 1 servers available will schedule both a start service on type 0 and a service on type 1. Again, as far as the event graph is concerned, that's that may be what you want, but that does not accurately reflect what's going on in the system. Okay, so that's kind of the key part here. And the way to drive this, notice that there's no inter-arrival of customers. But again, so this would be driven by, say, an arrival process that would schedule the different arrivals. Okay, is that kind of clear? Okay, and I don't know if you've been downloading the slides. As you can see, that there are some corrections I need to make. I will make those corrections and upload the correct one. Okay, containers. So this it is in their initial form, event graphs just had scalar state variables, but it turns out that having containers, meaning things like sets and lists and things like that, can be very useful to hold information, specifically state. So in our example here, what we notice is that Little's law notwithstanding, our basic multiple server queue model cannot directly compute things like the delay in the queue for each customer or the time in the system for each customer. And that's built into the simplicity of the model, because we're not actually representing each customer as an individual. We're actually just counting them. So, but in our example, supposing we were allowed to have a FIFO, first in, first out queue containing the customer arrival time. And by queue here, I mean the data structure queue. Think of a linked list or a sorted set or something like that. So maybe think of a sorted set in this particular case. So the idea is that as this queue, this sorted set, is going to contain the customer arrival times. And so now we're actually going to start moving towards representing each customer as an individual. Okay, so we want to explicitly tally the customer times, and the times are the delays in the queue and the times in the system. Those are things that in the first homework assignment that you were computing by hand. And as we noted, the multiple server queue model could not do that on its own on the computer. If you remember, what you had to do to figure that out is you had to look through the entire sequence of events and figure out, okay, the first customer came in here and started service here. The second customer came in at this time and started service at that time, et cetera. So you had to look through the entire sequence of events. It was not enough to just look at the last thing. Okay, so parameters, the same thing. Again, we're going to do this in a component way. So we're going to assume that we have an arrival process or some component that produces arrival events. And so all we need are the service times and the number of servers. Again, this is the same parameters as our multiple server queue. But now, okay, so starting with our states. So the number of available servers, that's going to be the same. But here, this little queue, that's going to be our first in, first out container of arrival times. And its initial state is going to be empty. The two additional state variables we're going to have are going to be the delay in the queue, and that's initial value is going to be NaN, not a number. Why? Because the delay in the queue really has no value until a customer begins service. So when a customer begins service, then there's a value for the delay in the queue, the time that between when they arrived and when they started. But until then, the delay in the queue really has no meaning. So its initial value is really undefined. And likewise, the time in the system, so that would be the time between when they arrive and when they finish service. And again, that's initially, I mean, it's not zero, it's nothing yet. Okay. So just to let's talk about these state variables and how we would get some statistics out of them, some metrics. So first, as we've seen, S, the number of available servers, is a time-varying state. And so we would estimate the mean by the average area under the curve. Again, this is something you've done by hand. This is something with the second computer assignment and the multiple server queue. That's something we use the simple stats time varying object for. So that's something that we've been working with. Now Q, this first in, first out container, this is also time varying, but its value are its contents. And so if we were to try to estimate the mean number in the queue, we would have to collect a time varying average of the area under the curve of the number in this state queue. And again, there's actually a class in SimKit that allows you to do that. However, here's where the difference are. D and W, the delay in the queue and the time in the system, are tally state variables. So this means that if we were to estimate the mean of D and W, we would do it in the quote normal way. In other words, we would add the delay. Let's say if we had 100 delays in the queue, we would add up their values and divide by 100. And likewise with W, if we had 1,000 times in the system that we'd observed and we wanted to find the average, we would add those up and divide by the number. That's, quote, the normal way. Okay, so let's look at events now. That is state transition. So we always start with the run event. So in this case, the number of available servers is K, how many we have. And remember, our queue is going to begin empty. So we clear it. Clear is, if you remember, is just says take everything out. D and W, we're initialized with NaN, again, as before, as specified, because at the beginning, they really have no value yet. All right, so now let's look at what's different about arrival. In the multiple server queue, we had just an integer queue, and when an arrival occurred, we just incremented that by 1. So instead, what we're doing is, remember, sim time. What is sim time? Sim time is just whatever time it is when this event occurs. And so we're going to add that value to this first in, first out queue. So this first in, first out queue is going to have these times of arrival. Now, start service, remember before, well, first of all, we decrement our number of available servers, but now what we had in the multiple server queue is we simply decreased queue by 1. We can't do that here because queue is a container and it's not an integer. So, and I say pop, that's basically where that's kind of an older way of saying just pop off the first value. So now what is that? When we start service, when this event occurs and we pop off the first, the smallest one in this container, that is the time that the customer who's starting service arrived. And so the difference between the current sim time and that time that we popped off is the amount of time they've spent in the queue. So we can get our state variable D, the delay in the queue, as being our current time minus the time that that customer arrived. Now for the end service, again, we incremented the number of available servers. That's something that we had done. But notice here, what we're doing is we're passing the time. And so what this argument is this is going to be the time that the customer who ended service, that's the time that they arrived. That's the time they showed up. And so the difference between our current time and when they showed up is the time that they've spent in the system. Okay, so now what we've done is we've said, okay, we need to convey that information to this end service event somehow. All right, how do we do that? Well, that's on the next slide when we start scheduling things. So again, arrival, we say if there's an available server, we schedule a start service. That's exactly as it was before. Let's look at this scheduling edge here. When we end service, if the queue is not empty, then we'll schedule a start service here. So before in the multiple server queue, the condition was queue bigger than 0. But again, that has no meaning for a container like queue, like this little queue. But we can say, are you empty? Or in this case, are you not empty? So if you're not empty, then we can schedule a start service, no problem. Okay, so the final scheduling edge here from start service is that when we start service, we do want to schedule an end service with a delay of a service time. Okay, so that's the same as before, but notice we are taking this local variable that we popped off our container and we are now passing it as a parameter to the end service. So remember, T over here in the start service was a local variable that represented the time that the customer who started service arrived, the time that the customer who's associated with this start service event, that's when they arrived. And we're passing that time that they arrived to the end service event so that when it occurs, it has the value of when that customer arrived, and so it can compute the time in the system, W. Okay, so the same letter T is used has 3 different meanings here, unfortunately. And I've tried it both ways, and the other way would have different letters for each one, and that causes one type of confusion. And using the same letter for all 3 does not cause that type of confusion, but can potentially cause another type of confusion. So be very clear about what the different T's are. They are different things. This T at the start service is a local variable. And so again, it's just a convenience for doing the computation. I mean, it's like a local variable for a method in Java. This T is a parameter, and it's a parameter on a scheduling edge that we're passing. So the local variable now becomes the expression that we're passing. And finally, this T is an argument of the event. So local variable, parameter, argument. Again, same letter, 3 different meanings. Okay, so that's any questions about the models that I've presented? Okay, everybody good. Okay, now I do have a few minutes to maybe I do have a few minutes to try and go back to our probability review. Let me find the slides for that. I forget where I was. Okay, so as I recall, we made it at least somewhere to here. Just to review, for discrete random variables, one of the key elements that help define what it is something called a probability mass function, or PMF. And that is defined as the probability that the random variable will equal x. So it's a function from the range of x, the random variable x, into the 0, 1 interval. And each value is the probability that it will equal that value. So again, just some examples: the flipping a coin, which is sometimes also called the Bernoulli random variable. And so it's either heads or tails, or the random variable, though, would be 0 or 1, because a random variable is always a number. So it's either 0 or 1. We've seen rolling a fair die. We have, if it's fair, then the probability of getting a 1, 2, 3, 4, 5, or 6 is 1/6 for each of them. We've seen the probability mass function of rolling 2 dice, again, fair dice. So the probability of getting a 2, there's only one way to do that. So we get a 1 and a 1. And so it would be 1/6 times 1/6, again, assuming they're independent. And so the probability of 2 would be 1/36, etc. Okay, so here's this is actually an example of what's called the binomial distribution, in this case with n equals 3. And a way to think of it is the counting the number of heads in 3 flips, where the probability of a head is equal to p. So again, if all 3 come up tails, then we have no heads. And so the probability of that is 1 minus p cubed, etc. So I believe I went through that. Now this is kind of a fun one, and actually an important distribution. This is actually sometimes called the geometric distribution. And one way to think of it or represent it is the number of flips of a coin where the probability of heads is p. It's the number of flips until we get a head. In other words, we're going to flip the coin until we get a head. So what's the range of this? It would be 1, 2, 3, or out to infinity. Okay, now what is the probability of getting a particular one? Well, it is p times 1 minus p to the x minus 1 for x. Okay, so just to look at this, it will be 1 if we get a head right away. So that's 1 flip, 1 head, and that's with probability p. So x, if you remember, any number to the 0th power, except for 0, is going to be 1. So that would just be probability p. Now we get a 2 only if we get a tail followed by a head, and that would be the probability of a tail is 1 minus p, and the probability of head is p. And for 3, the only way to get it would be 2 tails followed by a head, and the probability of that would be 1 minus p squared, etc. So the more tails we get at the beginning, followed by a head, then we just keep accumulating the 1 minus p squared. And it's important to see the difference between this and this situation, where if we're just counting the number of heads in a fixed number of flips, then, so for example, for x1, we have 3 possibilities. In other words, the head can come up anywhere here. But if this were, if we were looking at the number of flips until we get a head, For this, for heads, tails, tails, that would be 1. Here it will be 2, and here it will be 3. Okay, so these are very different. That's why this is a different probability distribution. This is the binomial probability distribution, in this case with n equal 3. In general, you just sort of have n, which is how many flips you are going to do, and then have a probability distribution, which would go from 0 up through n. Here, the geometric, we have the fact that there's no upper limit to it. Okay, so just in general, these probability mass functions are there are infinitely many of them, but important properties. First of all, p of x is always between 0 and 1. It could equal 0, it could equal 1. And the sum of all over the range of our random variable is always equal to 1. Okay, so we have a function whose values are between 0 and 1 inclusive, and whose sum is equal to 1. And any function that satisfied these conditions is a probability mass function for some random variable x. And as an exercise, I asked that you verify that these properties hold for the probability mass functions in the previous slides. And as I mentioned, some of these have names. So the Bernoulli random variable is the one where we were just flipping the coin once and seeing whether it's heads or tails. The binomial with parameter n and p, again, we saw an example there where n was equal to 3, but just in general, this is the probability mass function where you have n, p of x, the probability mass function evaluated at x, is n choose x times p to the x times 1 minus p to the n minus x, and that's for x equals 0 up through n. And again, and n choose x, if you remember, if you've ever seen this before, well, first of all, is n factorial over x factorial times n minus x factorial. Or if you remember, x factorial is x times x minus 1, x minus 2, et cetera, all the way down to 1. And then finally, we have the geometric, which was what we had just talked about before. This is one. Sometimes the geometric distribution is characterized by the number of tails until you get a head, or number of failures until you get a success. And there, just everything would be 0, 1, 2, 3, et cetera. And this would just be 1 minus p to the x. Again, it doesn't really matter. So just some, oh, I see I've gone over time here. So, okay, so we'll pick this up next time. And if there are no further questions, I will see you same time tomorrow.
Hey, sir. Were you going to fix the slides and upload them?
Yes, I will do that immediately.
Sounds good. Thank you, sir.
Yeah,
Have a good
my
one.
apologies for that.
No problem. All right. Take care.